So I carefully design A and B have the equal number of computation. So GPUs like this GPU is like almost 4 times faster compared to CPU. So execute 1 dot on the GPU is almost equal to 1 dot on the CPU. On this case, we show that the backend engine is able to parallel all this computation for you. So you can run CPU and GPU independently. So yeah, okay, so this is the last advanced usage I'm going to say about the array. Next, I'm going to move to the symbolic, another very important thing. So it's more about the neural network, because now currently you see that ND array just a scientific tensor, or n-dimensional array just a computation library. You have GPU and a lazy evaluation support. Next, I'm going to show why MXNet is good for deep learning. So in case someone just come in a minute, if you want to run the lab, you can go events-aws.quicklab to register account. Then you open the classrooms 6660 to start the lab. So we can try all these examples by your hand. Next, I'm going to show. So symbol is another important classes on the MXNet libraries. So it presents a multi-output symbolic expression. So you can think it like a function. So then you can compose a symbol by operators.
Can I ask a question about ND array?
Sure.
Yeah, so when I work with Iterator, sometimes I want to check or look at the individual results. So it says lazy evaluation. Is there any way that I can explicitly see what's the result of some intermediate array?
Yes. So sure. So the question that if you want to, for example, you want to step-by-step debugging, you want to see any result. So the thing that if you want to see that, I block at that time to print the result. If you do not see that, I can run in parallel. I can run as on the fly. So I'm going to show this is also the major difference between ND array and the symbol. So why I call that a user don't necessarily to know this is lazy evaluation. So this is just optimization. It didn't affect any user experience. So this is very different to the symbolic thing I'm going to discuss here. So this is why MXNet called MXNet. We provide 2 kinds of different front-end language. So let's go back to a symbol. It's a little bit more thing here. So a symbol is an expression. You can compose expressions. For example, you can compose by some basic matrix operations such as plus. You can also compose by using different neural network layers, for example, convolution layers. And then each operator can take several input variables. You can output several output variables. You can maybe have some internal state. Some particular neural network layers maybe have some internal state. And then a variable can be either free, that is, we didn't give anything to the variable yet, it's an empty variable, or you just output of another symbol. So this is a basic description of the symbol. Let's look at how it works by example. So this code shows we construct a very simple A plus B on MXNet. We first create a variable with a string length called A. We also create a variable B on a string length called B. And then we construct a C equals to A plus B. We print a tab. It's a symbol. And the C name, so in the previous 2 cases, we already give the variable a name. But if we do not give this one, the system will automatically generate a name for you. So this name is very useful to, if you have very complex computation graph, you can identify this variable by just giving the names. We will show it later. So up to this point, this is just a symbolic expression. We didn't give any data to this point. Now we can do some inference here. So for example, we can list all these input variables. We call it arguments. Or we can print all this output, what the output of the symbolic. And then if we give, okay, so let me show the result here. So all this input is called A and B because we give the variable name A and B. And also the output print out. The output is like the generated name for you. So then next, I can give the input and the input of the shape. We still didn't get data yet. We just inference the attribute. It tells you what the shape the input will like. And then I'll tell you, okay, this is the output shape we're going to have. So the last one I give A shape with 2 by 3, B shape 2 by 3, and then the output is also B 2 by 3. So this is useful if you have very complex neural network structures. You didn't give data yet, but you want to inference all these shapes. You can do memory allocations. You can do memory optimization for you. You can also calculate whether or not this can be fit into a particular GPUs, whether that just allocate and they crash. So this is not so nice. So next, I'm going to run these expressions. So the first thing I'm going to do that I need to give the free variables A and B actual data. And also we're going to show which devices is going to be run. So this is called a bind here. So in this example, this is the symbolic thing we constructed before. We give a context. We say, okay, run on CPU, and then tells you the variable names by A have an input is like a 2 by 3 matrix, B is 2 by 3 matrix, and then it returns the executor. So executor can run the forward pass. So you can run the forward to evaluate these expressions, and then it tells you, okay, and then you get the output attribute, they get the actual attribute. So it tells you the number of attributes is 1, the value is 2, all these 2. Also, we can bind the same thing into a different devices given different data. So we bind them into a GPU given different data on GPU, then it also can be evaluated here. Similarly, we can load and save a symbolic. So it's similar. The interface is similar to ND array, but the difference here, comparing to a binary format with a JSON format, we define a symbolic symbol, and then we can call the toJSON to get the symbolic representation of the thing. So also similar to ND array, this can cross different languages. So for example, you can write a expression in Python, then because it's easy to write, and then you can get this JSON format to let it run on just the C library. So for example, usually we can hack a bunch of things. We can train different things by easily using Python. If we want to go production, so we can just get the internal representation to send to just a pure C library. So it runs optimized well on the front end server usually. Also, you can write in Python and run in JavaScript. So all the things run on the browser. So up to this point, you can think, okay, symbol is pretty close to a ND array we have. We can define a bunch of tensor operations, and the only thing that you need to bind the data, you can construct the expression earlier, bind the data later, you can execute this one. But actually, this is a big difference. There's a nice document right by Tianqi, you can refer to read it. So this is 2 kinds of different programming flavors in deep learning. So the ND array we call the imperative programming. You write a sentence, run it, you get a result. You run the computation, get a result. The symbol is almost like a symbolic programming. So in this case, it's very similar to regular expression. You define regular expression first, compile it, and then run the result. Or you define a SQL sentence first, and then you can run later. So the reason why we have 2 things here is clear that for ND array, it's pretty straightforward. It's easy to work with some Python language features, such as you want to run it with for loop, if else conditioning, and some if you want to interact with NumPy. Or you can do step-by-step debugging. So this is the previous question I asked. But for symbol, because you define the symbolic thing, at the same time you construct the symbolic thing, you didn't run that yet. You need to get data later. So it's less straightforward. But it has more advantages here. first, the symbol have all this functionality of ND array, such as basic operations, reshaping. The second way that it has a bunch of neural network related symbols, such as we can define a convolution layer, we can define activation layer, we can define batch normalization layer. So the third thing is more important, that it have automatic differentiation. So if you run the neural network, if you train that, you want to get the gradients. Once the neural network is too large, it's pretty hard to get what the gradient function looks like. But once you construct the neural network using the symbolic interface, we can automatically do the differential for you. So you can return another symbol just to calculate the gradient. And the other thing that, because you can construct a different thing like a graph or like a function, so it's easy to construct manipulate complex neural networks. The last thing that is easy to load, save, and to port into different front end. And finally, you can have more optimization opportunities, because if you run that one, the backend engine already know what exactly computation you want to run, so you can do very complex optimization, such as what SQL database did for SQL. So we do have two kinds of things here. So we typically use ND array for works like a data containers. The data works on CPU, works on GPUs, or you can, if you want to write some very easy to write programs, such as you want to update, how to define updating rule in the optimization method, I'm going to show later. And also, you can use ND array to implement a symbol operator, so to implement complex neural network layers. But for symbol, it's mainly used for defined neural networks. I'm going to show later. So here, the next session, I'm going to show a define a simple neural network in MXNet and run that one. So we do a very simple one, just the multi-layer perceptions. As you know, just a chain of multiple fully connected layers. So this is the definition of the neural network. We first define the data. This is what the input data goes to here. Then connect this data with a fully connected layer. Let me run that first. So we first define a data, then connect to a fully connected layer, then do an activation, is a ReLU activation, connect to another fully connected layers. So the hidden size is 10, this hidden size is 128, and then we connect to a softmax loss function. So this is, we train different things together, and the type of the network is just a symbol. We can visualize this network as following. This is a little bit thing comparing to the basic operations we have. A neural network usually have multiple input and multiple output. So let me show here. So for this network, I list all this input argument. This is not bound with data yet. So we have a fully connected layer. The second fully connected layer is called FC2. It have a weight, and also it have a BIOS. So each weight input a BIOS. So also for the first fully connected layer, you have a weight, you have a BIOS. And also we have data. This is a training example comes to, and the label. This is required by the softmax loss function, the last layer you require to get the label. So, and the output is just the output of the softmax layer. So now, before I go start, I generate a synthetic data to train this particular neural network. So I can skip all the things for you. So it's basically using NumPy to generate a synthetic data. I can visualize this one. So I generate very simple 5-class classification examples here. So this is what this code do. So next, remember that for each net we have a bunch of unspecified free variables. So we can bind with data as usual, as just we do before. But here we use the simple bind function. the simple bind function, tells you what the context you want to run, and the data. This is the only output of the only input data, tells you the shape. This is how many the batch size you're going to use, and the number of features you have. So this net will inference all the shape for you and create all this required free variable content for you. So once we get the executor, it also returns the executor. So once we return the executor, the next thing we're going to do is initialize the weight. So this is the name, the name of all this input variable of the net. And this is the argument, this is the ND array we already created by the simple bind. We bind this together. Let me show how it works. I think I can split this one. Okay, split this cell. So this is the weight, the input weight, and it already creates an ND array matrix for you. And this is another weight, it already creates an ND array for you. So the next step, we're going to initialize the weight. So because we len the weight, the parameters by that the underscore weight, and the BIOS by underscore BIOS. So using the len, we can know what kinds of parameter you have. So if it is weight, we randomly initialize with random values. If it's a BIOS, we just give it to 0. So once we do that, we can train. So I just write a training loop here to show how it works here. So the first loop is like iterate 100 times. So then we get the data from the toy data we generated. Next time, because the argument is a dictionary now, we know the data len is data, the label len is out label. So then we copy the X into the binding the variables, copy the label into it. So once we get the data, we can run the forward pass. So we specified it is training, so we want to store something else for the gradients. So this is to a forward pass to get the output. Then we run a backward pass to get all these gradients. So this functionality is that we generate the gradients symbolic expression for automatically for you and run the gradients. So the good thing about that, you just specify the neural network and all these things runs automatically. Sorry. So then this sentence is like, this executor, this is the input arrays, the weight arrays, and this is the gradients you have. So the backward compute all the gradients stored here. So what we do is that we zip, we just make this one pair to pair. So for each weight and the gradient pair, we just update the weight equal to -2 learning rate times the gradients multiplied by a batch size. So what you can see that the last one is that for each 10 iterations, we get the output, convert to a NumPy to the argmax to get the predicted label, and convert to a NumPy and comparing to the NumPy to sum to get the accuracy. So this is basically to print the loss function. So what you can see here is that we work together with the symbolic expressions. This is how we construct the net, and also using ND array to interactively work together. So the ND array first look at the data containers to fit with the data. Secondly, with the basic operators to define some very natural way like a NumPy. A very nice thing about that, remember we have lazy evaluations. So this forward just also push these operators into a backend engine. The backward also push the operators. So up to this point, we still didn't execute anything yet. So up to this point, we just push all these operators into a backend engine. So we can just go through here. The only thing we block is here for every 10 iterations. So we need to make the output into a NumPy, convert it into NumPy to show something, then the thread block here into print something. But But the current backend engine already get the last 10 iterations for all these operations you have. So then you can do automatically parallel for you. So in this case, if you write a multiple GPU or even multiple machine program, you just work as this way. So even it looks like it's just a write serial program, but the backend engine can optimize for you. So for example, if I want to have a multiple GPU, I can show a basic feeling is here. So for example, if I have, if you have, for example, 4 GPUs here, what you can do that I need to create. So in 4 GPUs, I create a executor for each GPU is bind to a particular MXNet or GPU.j. So I bind, so this is a net, the single net, the simple bind. Okay. So I've skipped these other ones. So for each GPU, I create execute on the GPU. Then here, so here is different that for each GPU, I need to define the arcs get from this particular executors. So then I bind this one with maybe it's a little bit hard here. So but the basic idea that for each data X, each GPU only got one of the, I split into 4 parts. The ith GPU get the ith part. So maybe you can, basic idea is here. So each GPU get just a single part of the input data. And then I can run the GPU here. So, and up to this point, I want to sum for each, the weight is going to be summed over all this weight from the GPUs, and I'll show here. So the basic idea that you just write a for loop, single loop. It looks like you just use a single series as programming, but what you do that, you just push all the operator into backend. We want to optimize all this parallel for you. So the basic idea is here. It's not working yet. So if you want to have multiple machines, the idea is simple. Just it can also track the dependency between multiple machines. Mm-hmm.
So you said that it was a lazy operations. So when was the execution triggered? Or how do you trigger execution?
Once you push it, it is already triggered. But once you push there, it already run. So if that one is ready to run, that you got all the data is already to run. You do not have a particular run here. So it's continuous. You can continuously push into backend engine. The backend engine will continuously run the thing for you. The only thing that when the result is not ready and you call it print, for example, it will be blocked at this point. So it's a little bit different if you use TensorFlow or Ciano there. So TensorFlow, you maybe have a session to specify when to run. So this is a basic example of how to train a simple neural network in MXNet. We already show just to write a few lines of code to write the optimization algorithm. So next, I can show more composites here. The first is similar to, probably I not go very detailed about that. You already show the ND array. You can concat the data, you can split the data, and you can reshape the data, and you can split the data. So I probably not go very detailed here. The only thing that you first define the neural network, and then you bind with data and they run. So they're very similar to ND array. The next thing I'm going to show how you to construct a very deep neural network in MXNet. A usual way that, for example, if you use a Google inception network, you have maybe 20 layers. Each layers maybe have 4 or 5 convolution layers. So you have a bunch of 100 of convolution layers. So it's pretty hard to one by one to construct this one. So what we usually do is that we modularize all these components. So we make a function to construct the basic modular, and then make another function to build another modular. Let me show you here. So first, I define a convolutional function factory to basically just train a convolution with the batch normalization, this is to accelerate the training, and then have an activation here. So this function returns a symbol to have these three components. Next, we're going to define the inception modular. This is take a while. So this is train multiple convolution layers, because for inception modular, you have four passes, and the two of them are pretty long. So here, so a few lines of code, you can construct the inception modular. So if you want to specify by hand, it's pretty hard actually. So this is an inception modular. Then you can train different inception modular into a complete neural network. I didn't show the thing here. So the basic idea is that this is a inception modular A, inception modular B, and the final thing, okay, you train multiple inception layer and A and B, and then you finally get the symbol. So comparing to you write 1,000 of product buffer code, so this is a little bit easier. So but it's not so easy still. So this is how we construct deep neural networks. Next, I'm going to show if some neural networks want to have multiple loss functions. So especially for NLP applications, you want to have multiple loss. One loss calculate one particular thing. So what we can do is that, because in default, we train different neural networks, we only have a single output. What you can do is that we can have a group function to group multiple output together. So here we define the data, the fully connected layer. So the output of this fully connected layers is go to the input of the next activation and go to softmax. But we can group this softmax with the output of these fully connected layers, and it returns another symbol which have two output. The first is the fully connected output. The second is the final softmax output. So in this way, you can calculate you can run a forward and backward, you get all this loss function for you. Okay, this is up to this point, this is the basic usage, how to construct different neural networks in MXNet. Next, I'm going to show some of the advanced usage. The first is to cast a tab. So in default, we use 32-bit integers, but sometimes we want to have a lower precision data for better accuracy and the performance trade-off. For example, if you know the rest of the Pascal GPU, the tester version have accelerated half float performance. This is 16-bit float. It have 2 times faster comparing to the 32-bit. If you use the Pascal GTX, this is a consumer card, you have different thing. So the story that it have 8-bit integers 4 times faster comparing to the float integers. So in these cases, maybe you want to run the whole network on a lower precision. What you can do that, we just we can cast the input of a layer to give different float, different tabs you want. So in this example, in default is float 32. I can cast it into float 16. Also we can, so we have an infer tab function to gives you what the input. This input is a float 32. We can cast it into a float 16. Or if you have inter 32, we can cast it into also float. So the second important thing that we already defined a bunch of neural network layers. But sometimes if we do research, we want to have new layers. A typical way, if you use Caffe, you need to write on C++. But nowadays, C++ is good. It's good for performance. But once you use it to Python, you never want to go back. So you can wait. No, doesn't matter. The GPU are running. I just can do something else. So in this case, so most of our layers are written by C++, but it turns out the users want to just writing layers in Python. So this is what we call customized symbol. So in this way, you can define your symbolic a layer, a particular layer, a new layer, just using the Python front end. Let me show you example here. So in default is that because for each layer, we just use the ND array as the input for the variable and the ND array for the output. So you can basically use the ND array for the functionality to implement a layer. This is what I mentioned before. But this example, I'm going to show something different. This is I'm going to use the NumPy to implement a particular layer. So let me go to the code directly. So for each layer, there are two functionality you want to have. One is the forward to compute the output of this expression, and the backward to compute the gradient. So here I'm going to show how to implement the softmax using the Python front end. So for this softmax, is a subclass of the operators, this MXNet operators, and the customer OP. So we first define a forward function, then a backward. The forward function is like whether this is a training, in the training, or just if it's true, it's on training. If it's false, it's on the prediction. So the request, you can ignore that now. So this is the input data. This is the input of this softmax, and this is the output. So input is just a list of ND arrays. Output is also a list of ND arrays. This is some other data. This is not necessarily needed here. So what we do is that we get the first input data. This is the X. So then we cast S to a NumPy. So we get the ND array data to NumPy. So then we do a prediction here. So why is the predict just using the NumPy operators? I trust you definitely can know what it is looks like. So these two sentences just the forward pass of softmax define the NumPy. The last sentence is that once we get the result, we construct into a ND array a tab and then assign to the output. So this request specify if it's add to this gradients or add to the output or just override this output. So you can ignore these sentences. The basic idea that once we get the data, we convert it into NumPy, and then we convert the NumPy data back into the output. Similarly, for the back end, so this is the gradient for the output. This is the input data, output data, and the input gradients. So you can do also run the gradient function here for this particular function. So this is a major computational function of these two. Next, I'm going to do that because the symbolic function support a bunch of inference of the shape, inference for the attributes. So we need to have another, the property classes. So it's called the customer OP property. So this property first register into MXNet that this function name is called softmax. We take this particular name. So you can change it to a different name as usual. Then it basically runs what is the argument you have, what is the output, the lane output that you have, and given the input shape, what is your shape, data shape for the output. And the last function create this softmax. This is just the class we defined the previous. To return the actual, the object can run the forward and backward. So up to this point, you already implement a customized OP. So how to use that is it's very simple. So you just it's basically like already predefined operators, but different that it's all by So by MXNet.symbol.customer. So the data tab, the input is like a previous input that you have. Then the operator tab is softmax. So this is because the lane you choose is softmax. You just give this string name and you can get it here. So so now you can just you use your customer's layers in the whole neural network definition. The final thing, I probably not go very detailed here, is that it's a little bit complicated. So when we create a symbolic thing, we want to pass, for example, pass additional information to the symbolic. For example, if you run model parallel for the program, we want to specify which variable will run on which GPU devices. So then we can attach a string pair to the symbolic to give an attribute. Another example is that for the training a neural network, we probably want to have a layer-wise learning rate. So to do that, we just attach a particular layer-specific string to the symbolic thing and run the update. We can get that particular string out and get a predefined learning rate. So this case is that using the Python front end, you can insert key string pairs into the C++ engine, so let the engine know what additional feature you have, and you can also get it back from the even a different front language. So okay, this is basically we covered what looks like of a symbolic expression and how to run basic things, how to construct a neural network, and how to train a complete neural network examples. We have a bunch of very interesting here. So if you use Torch before, but not so happy about the Lua, so we can actually run Torch within MXNet. So I'll not go very detailed here. So once you install Torch, you can just call, for example, you can call the Torch operators using the Python binding, or use even different binding, Scala binding, for example, using the Torch operators. Or you can use a Torch modular as usual. This is also a symbolic thing. You call the Torch modular, you specify the data, and you specify the Lua string, oh, this is the actual Torch modular we are going to use. And then you something about that. Similarly, if you are a fan of Caffe, but you still want to use MXNet, for example, for the distributed training, for example, we have a bunch of users actually have Caffe runs before, but if you want to run a distributed setting, you can just port the Caffe code into MXNet. So, for example, in the Caffe code, it's called Caffe operators. So you can even specify what the proto-text you have in the Caffe, and then define a network. Then you can use the same thing, you can run a distributed setting. Okay, so this is almost like done with a symbolic interface. The last I'm probably going to say is a simple example how to run a matrix factorization. So this is more close to the KDD community. So here I'm going to run is not very standard matrix factorization. It's a little bit change to show the flexibility of using MXNet. So as we know, in recommendation systems, we want to inference the latent variable about users and items. So for each user, so for example, we want to predict the rating of user I to user J. We can just learn a vector about the user I and a vector about the user J, and do the inner product to get the rating, to approximate the rating. So we can definitely learn this embedding directly. This is just the SVD. You given the rating matrix, we perform SVD, and then we get the latent vectors. But here, we also show that you can also try use a neural network to run that, not directly run that. You can maybe have stack multiple layers to run that embedding. I'm going to show in this example. So, but the basic idea is that we're going to show how to use MXNet to construct a basic factorization machine, even a more fancy one. It's not going to be the state of the art. I just writing that one last night. I didn't repeat the state of the art result yet. Also a little bit slower what I expected. I will work on this this week to get the start of the art result. So here I'm going to use the movie length data set. So basically, I think you definitely know well about this data set. So each row of this data set is about a user ID, a movie ID, and the rating of this user to that movie, and the timestamp. We don't need the timestamp here. So here I show completely examples to write a program in MXNet. Usually we don't need necessary to write all these modules. It's already predefined. But we're going to show how write a completely thing just based on the ND array and the symbol interface. The first one, we define a data batch. So we're going to run SGD. So each SGD it take a batch of just the tuples, your user item rating tuples. So this data have tells the MXNet, okay, what the data length, the data, the length and the shape, and what the data length and the shape. So this is just a single batch. I duplicate the thing here. The next thing, I define the iterator. So iterator each time returns a batch of the data. So here's a very simple iterator. So each time the init function just open the file, read all the file into memory. And so this file have the first column is user, the second column is item. The last score is called a score. We call it just given a name. And this is a shape of the user. And for if you stack batch size users, we get a batch times 1 array, and also the item or the score. So for each iterator, we just return a batch of a particular size. So I can skip this one. And for each reset, we finish one iteration, we randomly shuffle the data. So this is about the data thing. And this example shows we download. Let me still run this one. We download the data. It takes 1 minute to download the data. So the next one, we find the maximum number of users and the maximum number of IDs here. So this is all about data prepare the data. Next, it's a little bit unusual compared to what we do, that I first define the training algorithm first, and then specify what the network we're going to use. So because for recommendation system, we use the RMSE as the arrow function usually. So I define the RMSE function here using, this is not NumPy, this is just an undo array. So given a score, given a label, given a predicted label, I just compute the root mean square error for this one. This is used for printing. Let me run this one. And then I define the trend. This is a bunch of, I didn't delete yet. Just work on this on last slide. So I copy this data actually from the image classification application. This is for training the ImageNet. So this is another module I didn't go detail very on this tutorial. This is the context thing, the context you want to run. Here I choose GPU 0. If you have multiple GPUs, you can definitely go a list of GPU you can have. It automatically do that for you. And the network I didn't define yet. This is how the model we're going to design. The number of data passes you want, the learning rate you have, there's a weight decay, you can ignore that. There's a momentum for the training, you can ignore that. So next I choose the batch size to be 64. This is each time I train 64 tuples into the training and get the data. This is the iterator we have. Then we can train. So the training data, the test data, this is how you evaluate use the RMSE, and this is to printing. So I print every 10,000 examples to get the speed. Okay, this is done. So next I'm going to show using different ways, different models in MXNet. The first is just the SVD. So now I'm going to define a symbolic expression to just get the SVD function, the basic SVD. So we first define the input is a user. This is the input data. An input of an item. This is for item, and the input for the score. This is for the input. The next thing, I know that there's maximum number of users, and I want the dimension, the embedding dimension to be k. So I create the embedding layer. So embedding layer, you create an input dimension times the output dimension matrix. So each time you give a user, it's just a look up the particular user out, get it out. So if the user I, you just get the i's embedding of this embedding layer. So similarly, I do for item. And then once we get the user and the item, we want to do the inner product. The inner product is just the element product and then do a sum. So we do element product and the sum over the axis 1 because the axis 0 is used for the batch. So, and then I probably can remove the flatten. So reshape into a 2D array and give it to a linear regression output. This is, it have, the data is the prediction, the label is the score, we're going to fit it back. So here we define the network, then we can train. We define here I use the embedding size to be 64, and the batch size to be also be 64, and train 10 data batches, and the learning rate is specified this one. So I can train that one. So this is how it's running. You can get all this result here. So what we can see is that you can say, okay, this is training on the GPU 0. For each, from time to time, print the speed, and also print the training. MSE is a little bit large at the beginning. So then I test on the test data set. It's large, and then I train the next iteration, decreases a little bit to 3 to 2.4, and it keeps decreasing, decreasing. It should be. The last one is 1.0 MSE. So I just look at the benchmark. It's not so great here. So what I can do is that I can increase the number of dimensions to increase the model complexity. This is the usual way. But I try something different here. So the thing I tried is that I add fully connected layers to the embedding layer. So before that, I just look at the embedding layer to get the user latent vectors. Now I add another fully connected layer to have another layer here. And then this output of the fully connected layers is used to predict the user. So this is, you can definitely go multiple, you can definitely go multiple fully connected layers. And you can also add some, I didn't add some activation here, so, oh, I didn't add the activation here. Okay, so doesn't matter. I should be. So here I try another neural network, 2 layers. The first embedding layer is 64, the second one is still 64. I try a batch size here and try to run that one. So it's going to be a little bit slower, but the MSE is much slower compared to the previous one. The previous is like a 3.7 at the beginning, but now we get a little bit better here. So then you can continue decreasing. And then finally, you can get some result. So finally, that you get the training accuracy. A training error is like a 0.9. The validation error is also 0.9. So what next I can do that I can change an embedding layer to probably a large one. Let me find. So I change to maybe 500, 1,000. Try what's going on there. It's still running. Then it looks like even better for the first time convergence. But the problem may be that, let me see. The problem that it's a little bit overfitting because this is a training error. This is the validation error. So this is pretty much larger compared to the training one. Well, this is also. So this is because we increase the model complexity. We have a bunch of overfitting here. So this is what we expected. Now it's go to, so 0.92, and but still 0.95. So a usual way that we can add the L2 norm to the weight. This is a usual way to do. I try to more like a neural network way, that is add a dropout layer to the particular neural network. So I show here. So add a dropout layer just after the fully connected layers. So even that, so it works like a regularization. So once you get the embedding layer, I just randomly drop. Randomly, in the half probability, I set the value to 0. So it works like a regularization. It's basically similar to the what before. We just added something here. So I will not. I can train that here. Still use a large one. Maybe I use a large one. What we can see? Let me see. Well, still a little bit overfitting. I think it's a little bit better. Let me wait until I finish. Well, it's done. So the final training error is like a 0.92, and the validation is like still a little bit overfitting here, comparing to no embedding. Oops. Well. Uh-huh. Sorry? Last line? Oh, yes. Thanks. So why the results are similar? Well, should be better. Mm-hmm. Yes. Yes. I already mentioned before that. So because I only have single GPU on this machine, I only try single GPU. So if you look at the context, the model fit for the context accept the list of devices. You can even use GPU, maybe 4 GPUs a single and the CPU. You can do that. So here I maybe try CPU here. I don't know. I didn't try that before. Let me. Let me first look at the result. So if you have multiple GPUs, you don't need to worry about anything. We just evenly split the training data to batch into several pods, and each pod goes to each GPU. But you use a CPU and a GPU together, because CPU is usually slower compared to GPU. I think we have option to specify the workload. Let me try. I think it's like a work load list. CPU is like 4 times slower compared to GPU. I can try here. Maybe it's just no dash. Let me find it. Okay, so this is a workload list. So it tells you. So if you go, all these documents, if you want to try, all these documents are on the MXNet.dmc.ml. You can look at, well, the screen is too. So if you go Python package, all the thing, so all this detailed symbolic, for example, symbolic interface, all these functions are available here. So also you can look at the Python code if you prefer. Workload list. So workload list. Yeah. So this specify the how fast each devices you have. Then let me finally look at the result. Well, so the training accuracy here is much larger compared to the validation accuracy. So this means the dropout layer actually works here. So if you compare to the output of the last one, so this training accuracy is much lower comparing to, but the validation accuracy didn't change too much. This means you need to more fine tune of the things. Next, let me try using two devices. Oh, wrong thing. I think it's probably on the fit option. I'll probably be let me forget this optimization, it's fine. Well, so here shows that using a CPU and a GPU, it's not optimal because CPU is slower compared to GPUs. So you cannot see too much acceleration there. But if you use multiple GPUs and if the workload is large, usually we can see on the slides there's a very clear speed up over there.
So if I use multiple GPUs that are identical to each other, just taking all the workload or evenly distribute the workload.
Yes. So if you specify the batch size to be 100 and use 4 GPUs, which means each GPU will get 25 batch, and then you compute the result and summation over all the gradient you have across all the GPUs. So you should do not see any convergence change between one GPU and the 4 GPUs. But the only thing that if the workload is pretty small, you need to pay the cost between GPU synchronizations. Usually, if the workload is large, for example, using deep neural networks, it's definitely fine. But if the workload is small, you maybe didn't see maybe 4 GPU didn't give you 4 times speed up.
So that's worth it to use CPU if it has like a 16 or 32 cores, multi-core CPU.
You mean using GPU?
No, because my CPU has like 32 or even 64 cores. Does it worth it to involve CPU relation? Because you said you use CPU here, but it does not show much improvement, performance improvement. But if the CPU is more powerful, like 60, 32 cores.
Yes. So here the problem here that this particular machine, the GPU is like 4 times comparing to the CPU, but now I evenly partition the workload into CPU and the GPU, so it actually should be slower. But I need to figure out the workload list. So you specify which part of example goes CPU, which part goes GPU, you definitely see a speed up. So if you have a high-end CPU and low-end GPU, I definitely see a speed up there. Even you have maybe 2 kinds of different GPUs. One is fast, one is that one you bought maybe years ago. So you can also use these 2 guys, but using manually specify the workload goes too well. So okay, so I think I'm also done here. You're going to, yeah, sure. Tianqi will show some more advanced examples here. Let me give to you. So this is